Before we begin, remember this phrase: one day, one universe, one perspective that changes everything. Welcome to Cosmic Calendar, one day of the universe where the entire history of the cosmos unfolds as if it happened in a single day, and where science becomes a story you can feel. What if everything you think you know about the Big Bang is incomplete? Not wrong, just told without depth, without emotion, without scale. Most explanations reduce it to an explosion. But the truth is far more unsettling and far more beautiful. The Big Bang wasn't an event inside the universe. It was the birth of space, time, and every possibility that would follow. In the next moments, you're not just learning science, you're stepping into the origin of Earth, the foundations of geological eras, the roots of life, and the long chain of extreme events that eventually made humanity possible. This is not abstract theory. It's the backstory of everything you've ever touched. Here's the bold idea most people never consider. The universe didn't begin chaotic. It began precise. Every imbalance, every fluctuation, every rule of physics carried consequences that still shape the planet beneath your feet today. As you watch, stay curious. Question what feels familiar, and allow the scale of the cosmos to recalibrate how you see time, science, and yourself. If this journey expands your perspective even slightly, engage with the channel. Like, comment, and subscribe to Cosmic Calendar. Each interaction helps this series reach others who are ready to see the universe differently. Now let's return to the very first moments, when nothing had a name and everything began. Before there was time, before space could stretch or light could travel, there was no before at all. The universe did not begin inside something larger. It began as everything, compressed beyond imagination. No stars, no planet, no Earth, no history of Earth, just a state where the laws of physics were pushed to their absolute edge. This is not a story that starts with an explosion in space, because space itself had not yet been born. In that first incomprehensible instant, the cosmos existed as a singularity. Energy, matter, and the forces of nature fused into one. Temperature and density were so extreme that our current physics struggles to describe them. Science doesn't romanticize this moment, but it does respect it. Every galaxy, every geological era, and every form of life traces its lineage back to this boundary of understanding. Then something extraordinary happened. Space itself began to expand, not into emptiness, but as emptiness came into being. This expansion was not matter flying outward through space. It was space stretching everywhere at once. The universe was not exploding from a center, because there was no center. Every point was the beginning, and in a sense, every point still is. As the universe expanded, it cooled, allowing the first distinctions to emerge. Fundamental forces separated, setting the rules that still govern extreme events, supervolcanoes, stars, and planets. The same physics shaping the early cosmos would one day sculpt Earth's interior, drive extreme events, and influence the fragile conditions that make the origin of life possible. Time itself was born in this expansion, not ticking like a clock, but unfolding as change became possible. Without time, there is no causality, no story, no science. With time, the universe gained a direction, a subtle arrow pointing from simplicity toward complexity, from uniformity toward structure. In this early universe, there was no light as we know it, only an opaque plasma where energy and matter were inseparable. Photons couldn't travel freely, trapped in constant interaction. Yet even here, the seeds of the cosmos were already being planted, encoded in tiny fluctuations. These fluctuations would later grow into galaxies, stars, and eventually planets like Earth. This moment reminds us of something quietly profound. Everything familiar, humanity, life, the planet beneath our feet, emerged from conditions that seemed utterly hostile to existence. The universe did not begin with balance or comfort. It began with extremes. And still, from those extremes, complexity was inevitable. As you move through this cosmic calendar, keep this first instant in mind. The forces shaping the universe today are not new. They are ancient echoes of this beginning. If this moment intrigues you, it connects directly to later episodes where we explore how matter cooled, how light was released, and how the groundwork for the history of Earth was quietly laid across the cosmos. In a fraction of a second after the beginning, the universe did something almost impossible to imagine. It expanded at an unfathomable rate, far faster than the speed of light, redefining scale itself. This phase, known as cosmic inflation, stretched space so rapidly that tiny quantum fluctuations were magnified. These fluctuations became the large-scale structure of the cosmos. This abstract concept explains why galaxies exist at all. Inflation wasn't chaos, it was precision written in extremes. Space didn't tear apart, it smoothed out. Regions once microscopically close were hurled vast distances away, creating a universe uniform in every direction. This is why the cosmos appears so balanced today, despite being born from such violent conditions. During this expansion, the universe became astonishingly flat in a geometric sense. Not flat like a sheet of paper, but balanced in a way that allows gravity, matter, and energy to interact just right. This balance was essential for planets, geological eras, and for Earth to form without collapsing or flying apart. Inflation also explains something deeply counterintuitive. The largest cosmic structures began as the smallest irregularities. Quantum fluctuations, usually confined to the subatomic world, were stretched into the scaffolding of the universe. The cosmos, in a sense, scaled up its smallest whispers into its loudest statements. As inflation ended, energy didn't vanish, it transformed. The universe reheated, filling space with particles and radiation. This set the stage for everything that followed. Matter began to take form and the universe transitioned from rapid expansion to a slower, more structured growth. This shift marked the real beginning of cosmic evolution. This moment matters because it shows that order can arise from instability. The same principle echoes later in science, when extreme events reshape planets or reset life's trajectory. Instability is not the enemy of creation, it's often its engine. Scale changes everything. The tiniest fluctuations determine the architecture of the universe, just as small changes on Earth define the fate of life. As you follow this cosmic calendar forward, notice how this early expansion connects to later chapters. When matter cools, when light is released, and when the universe becomes transparent, each step builds on the last, and inflation is the reason there was room for any of it to happen. As inflation ended, the universe did not drift quietly into calm, it transformed. The immense energy that drove expansion was released into space, reheating the cosmos and flooding it with particles. This wasn't fire in the ordinary sense, but a universe-wide awakening where energy became matter everywhere at once. In this newborn heat bath, the universe was a dense, seething plasma. Quarks, leptons, and force-carrying particles collided relentlessly, forming and annihilating in a restless equilibrium. There were no atoms, no nuclei, no structure, only a storm of potential governed by precise laws of science. This era set the rules that still define the universe today. The relative strengths of forces, the masses of particles, and the balance between matter and radiation were locked in during these moments. Without this delicate tuning, planets, geological eras, and even Earth itself would never emerge. Matter began to gain a slight advantage over antimatter. For reasons still studied in modern physics, matter survived in tiny excess. That asymmetry, almost nothing in numerical terms, became everything. Every galaxy, every planet, and every trace of life depends on that early imbalance. As the universe expanded and cooled, particles slowed down enough to persist. Quarks bound together into protons and neutrons, forming the building blocks of all future atoms. The raw ingredients of stars and planets were now present, even though darkness still filled the cosmos. There is something quietly humbling here. The complexity of humanity traces back to a time when nothing recognizable existed. Before oceans, before supervolcanoes, before extreme events shaped Earth's surface, the universe had already decided what could exist and what could not. This phase reminds us that creation is not sudden perfection, but gradual permission. The universe didn't rush toward life. It patiently assembled the conditions for it. Science reveals this not as coincidence, but as consequence. As the cosmic calendar moves forward, this particle-filled universe will cool enough for the first nuclei to form. What began as pure energy is preparing to become substance, setting the stage for light, atoms, and eventually the long history of Earth itself. As the universe continued to expand, it cooled enough for a quiet but decisive transformation to occur. Protons and neutrons, once too energetic to stay together, began forming the first atomic nuclei. This brief window is known as Big Bang nucleosynthesis, and it shaped the elemental foundation of the cosmos. In just a few minutes, the universe produced hydrogen, helium, and traces of lithium. Nothing heavier could form yet. The conditions changed too quickly. Still, This simple chemical recipe would define everything that followed, from stars to planets to the long geological eras of Earth. Hydrogen became the universe's most abundant element, the raw fuel of stars. Helium followed closely, stabilizing stellar cores and influencing how galaxies would evolve. These early proportions were not random. They were dictated by temperature, density, and time with extraordinary precision. Once this process ended, it would never happen again on a cosmic scale. The universe cooled too much, and nuclear fusion shut down everywhere at once. From that point forward, heavier elements would only be forged inside stars or during extreme events like supernovae. This moment explains why the cosmos looks the way it does today. The chemical simplicity of the early universe made stars inevitable. Without abundant hydrogen and helium, there would be no long-lived stars, no stable planetary systems, and no Earth capable of sustaining life. There is a quiet elegance in this restraint. The universe did not rush to complexity. It paused at simplicity, allowing time to do the rest. Science shows us that limitation, not excess, often creates the most enduring structures. Long before oceans, supervolcanoes, or the origin of life, the universe established its basic inventory. Every atom in your body, except hydrogen, would one day be recycled through stars, but hydrogen itself is a direct relic of this ancient phase. As the cosmic calendar continues, these simple nuclei will wait in darkness for hundreds of thousands of years. Light is still trapped, but the stage is nearly set for the universe to become transparent, revealing its earliest visible echo. After the first nuclei formed, the universe entered a long, unfamiliar silence. It was filled with energy and particles. Yet no light could travel freely. Photons were constantly scattered by charged particles, trapping radiation in a dense cosmic fog. The universe existed, but it could not yet be seen. Matter and radiation remained tightly coupled. Electrons moved too freely, preventing atoms from forming. Every attempt at stability was immediately undone by heat. The cosmos was expanding, cooling, and waiting, governed by unhurried but relentless physical laws. This darkness was not emptiness, it was preparation. Gravity was already at work, gently amplifying tiny density variations. These subtle differences would later grow into the large-scale structures of the universe, influencing galaxies, stars, and planets. Time passed on a scale difficult to grasp. For hundreds of thousands of years, the universe remained opaque, glowing invisibly in every direction. No geological eras, no life, no extreme events, only a patient cosmos, moving toward its next threshold. This stage matters because it shows how delay can be essential. Had atoms formed too early, structure would have been washed out. Had they formed too late, gravity might never have gained a foothold. Science reveals a universe balanced not by chance, but by timing. Even here, the future history of Earth was quietly being shaped. The same gravitational rules guiding invisible matter would later sculpt continents, drive mantle convection, and enable supervolcanoes. To reshape the planet's surface billions of years later, there is something deeply instructive in this unseen era. Progress does not always look like motion. Sometimes it looks like waiting under precise conditions, where change is subtle but irreversible. As this cosmic calendar advances, the universe is approaching a turning point. Electrons are about to settle down, atoms are about to form, and light, long trapped, will finally be released, carrying a message that still reaches us today. As the universe cooled further, it crossed a decisive threshold. Electrons slowed enough to bind with protons, forming the first stable atoms. This process, known as recombination, changed everything. For the first time, matter became electrically neutral, and light was no longer trapped. Photons, once endlessly scattered, began to travel freely through space. The universe became transparent. What had been an invisible glow turned into a faint, enduring signal that still fills the cosmos today. This released light is not a metaphor. It is measurable evidence of the universe's early state. That ancient radiation has cooled over billions of years and now appears as the cosmic microwave background. It is a nearly uniform echo of the Big Bang, carrying tiny temperature variations that map the universe's earliest structure. Science reads this pattern like a fossil record of the cosmos. These subtle irregularities mattered enormously. They marked regions where gravity would later gather matter, forming galaxies and stars. Without them, the universe would remain smooth and empty, with no planets, no Earth, and no history of Earth to tell. Recombination did not create complexity, but it allowed complexity to begin. Light became a messenger no longer confined, capable of traveling across the universe. Every telescope today is, in a sense, still receiving this first release of cosmic information. This moment reminds us that visibility follows readiness. The universe did not reveal itself until conditions were right. In science, understanding often works the same way. Clarity arrives only after long preparation. Long before life, before geological eras and extreme events reshaped Earth, the universe learned how to be seen. The same physics that freed light then continues to guide radiation, energy flow, and planetary climates now. As the cosmic calendar moves on, gravity will take center stage. With light free and matter neutral, the universe is ready to build structure, slowly pulling itself together out of its own vastness. Com a luz finalmente livre para viajar, o universo entrou em uma nova fase impulsionada não pelo calor, mas pela gravidade. A matéria, agora neutra e menos energética, começou a responder mais fortemente às sutis diferenças de densidade impressas há muito tempo. Esses pequenos desequilíbrios, quase insignificantes à primeira vista, tornaram-se as sementes da estrutura. A gravidade trabalhou lentamente, puxando pacientemente a matéria para regiões ligeiramente mais densas. Ao longo de imensos períodos de tempo, nuvens de hidrogênio e hélio começaram a engrossar. Ainda não havia estrelas, nem galáxias, apenas vastas e escuras concentrações de gás crescendo mais pesadas sob sua própria atração. Isso não era o caos se desenrolando, mas a ordem emergindo da simplicidade. A ciência mostra que a gravidade não precisa de direção ou intenção. Com o tempo, ela amplifica naturalmente as diferenças, transformando um universo quase uniforme em um rico em estrutura e contraste. À medida que a matéria se reunia, a matéria escura desempenhou um papel crucial. Invisível, mas influente, ela forneceu andaimes gravitacionais, guiando a matéria comum em filamentos e nós. Essas estruturas ocultas definiriam mais tarde onde as galáxias se formam e onde permanecem os vazios cósmicos. Esta fase estabeleceu limites que ainda moldam o universo hoje. A arquitetura em grande escala do cosmos, a teia cósmica, remonta diretamente a esta era tranquila. Cada galáxia, cada sistema estelar e cada futuro planeta foram restringidos por esses padrões gravitacionais iniciais. Aqui o universo demonstra algo sutil, mas poderoso. O crescimento nem sempre se anuncia com violência. Algumas das mudanças mais importantes se desenrolam quase invisivelmente através do acúmulo e não da força. Muito antes de a Terra desenvolver eras geológicas ou experimentar eventos extremos, a gravidade já estava elaborando o projeto para os mundos que viriam. A mesma força que reuniu o gás primordial um dia governaria as órbitas planetárias, o estresse tectônico e até os ciclos que influenciam a vida. À medida que o calendário cósmico continua, essas nuvens em crescimento atingirão um ponto crítico. A pressão e o calor aumentarão, e as primeiras estrelas, motores cósmicos de luz e química, finalmente se acenderão, encerrando a longa escuridão do universo. After millions of years of silent accumulation, gravity crossed a threshold. Dense clouds of hydrogen and helium collapsed inward, heating as pressure intensified. In their cores, temperatures soared high enough to ignite nuclear fusion. The first stars were born, and with them, the universe experienced light in a new and transformative way. These earliest stars were unlike anything that exists today. Massive, short-lived, and extraordinarily hot, they burned their fuel at a furious pace. There were no planets around them yet, no life, no Earth, only raw stellar power reshaping the cosmos. Their light pierced the darkness, ending the universe's long night. Inside these stars, something revolutionary occurred. Nuclear fusion forged elements heavier than hydrogen and helium for the first time. Carbon, oxygen, and other foundational ingredients of life were created in stellar cores, proving that chemistry itself depends on stars to evolve. When these massive stars died, they did so violently. Supernova explosions scattered newly formed elements across space, enriching surrounding gas clouds. Extreme events like these did not destroy possibility. They multiplied it, seeding the universe with material complexity. This was a turning point for science and for the cosmos. The universe was no longer chemically simple. With each stellar generation, matter became more diverse, opening pathways toward planets, geological eras, and eventually the origin of life on worlds like Earth. There is a quiet lesson embedded here. Creation often requires sacrifice. The first stars did not survive long, but their brief existence made everything else possible. Without their collapse, the universe would remain barren and lifeless. Long before humanity could look up and ask questions about the cosmos, stars were already answering them through physics. They were shaping the conditions under which planets could form, and life could emerge billions of years later. As the cosmic calendar advances, these stellar remnants will gather into larger systems. Galaxies are beginning to take shape, organizing light, matter, and time into structures that endure. As generations of stars lived and died, gravity began organizing them into vast rotating systems. Gas, dust, and stellar remnants gathered along invisible frameworks, forming the first galaxies. These were not yet the graceful spirals we see today, but crowded regions of intense activity. Inside these early galaxies, star formation accelerated. New stars ignited from enriched gas clouds. These clouds were now filled with heavier elements forged in earlier stellar deaths. Chemistry was becoming more complex, and the universe was moving decisively away from simplicity. Galaxies grew through interaction and merger. Collisions were common, reshaping their structure. These events triggered waves of star birth. Extreme events were fundamental to how the cosmos matured. Within galactic centers, gravity reached extraordinary strength. Massive concentrations of matter formed. Some collapsed into black holes that influenced their surroundings on colossal scales. Energy, radiation, and motion became tightly linked in ways science is still actively studying. This era matters because galaxies are more than collections of stars. They are ecosystems of matter and energy, capable of sustaining long-term evolution. Without galaxies, stars would drift apart and planets would struggle to remain stable. The future history of Earth depends directly on this stage. Our planet exists because it formed inside a galaxy that provided heavy elements, stable orbits, and time. Geological eras, life, and humanity all rely on galactic order established billions of years earlier. There is a deeper pattern here. Structure emerges not by avoiding interaction, but by enduring it. The universe grew more organized through collision, tension, and redistribution, not through isolation. As the cosmic calendar continues, these galaxies will mature. Within them, calmer regions will appear, allowing stars like the Sun to form. These stars are surrounded by disks, where planets can finally take shape. Within mature galaxies, not all regions remained violent. Some pockets grew calmer, allowing gas and dust to settle into rotating disks around young stars. These protoplanetary disks became cosmic workshops, where gravity and motion worked together to assemble solid worlds from scattered material. Dust grains collided and stuck, slowly growing from microscopic particles into rocks, then into planetesimals. Over time, these bodies merged through countless impacts, forming the cores of planets. This was not a smooth process, but a persistent one driven by repetition and time. Closer to their stars, rocky planets took shape, forged from metals and silicates. Farther out, where temperatures were lower, gas giants accumulated thick atmospheres of hydrogen and helium. The architecture of planetary systems began to reflect both physics and distance. These early systems were unstable by modern standards. Orbits shifted, planets migrated, and collisions were frequent. Extreme events were common, reshaping surfaces and determining which worlds survived. Yet this instability was essential for long-term balance. Here the future history of Earth quietly enters the story. Our planet formed in one such disk, within a galaxy enriched by generations of stars. Its position, mass, and composition were not guaranteed outcomes, but consequences of universal processes repeated countless times. Geological eras would later record the memory of this chaos. Through impacts, volcanism, and internal heat, supervolcanoes, tectonics, and atmospheric evolution all trace back to how planets assembled and cooled in their earliest moments. Science shows that planets are not rare exceptions. They are natural outcomes of star formation. Wherever disks exist, worlds tend to follow. This realization reshapes how we think about life and humanity within the broader universe. As the cosmic calendar moves forward, one of these planets will become our focus. Among countless worlds, Earth will begin its long transformation, from molten beginnings to a place capable of sustaining life, history, and reflection. Among countless forming worlds, one planet began a particularly complex journey. Earth emerged from collisions, accretion, and internal heat, growing layer by layer as gravity pulled material inward. In its earliest state, it was a molten body, shaped by impacts so violent they redefined its structure. Heat dominated everything. Energy from formation, radioactive decay, and constant bombardment kept Earth in a near-liquid state. Heavy elements sank toward the center, forming a dense core, while lighter materials rose to create a mantle and primitive crust. This differentiation would later control magnetic fields, tectonics, and long-term stability. The young planet experienced extreme events on a scale difficult to imagine. Massive impacts reshaped its surface repeatedly, including one that likely formed the Moon. These collisions were not anomalies. They were part of how rocky planets matured across the universe. As Earth slowly cooled, its surface began to solidify. Volcanoes dominated the landscape, releasing gases trapped deep within the planet. Through relentless outgassing, an early atmosphere formed, laying groundwork for future climate and chemical cycles. This was not yet a world of oceans or life. It was a dynamic system of fire, rock, and motion. Still, the processes unfolding were essential. Geological eras had not begun, but their foundations were already in place, written into Earth's interior. Science reveals a crucial pattern here. Stability is often born from chaos. The same forces that once made Earth hostile would later make it habitable. Without early instability, there would be no long-term balance. The planet was learning how to regulate itself, how to recycle material through mantle convection, how to store heat, how to evolve slowly instead of collapsing or freezing. These traits would become decisive for life. As the cosmic calendar advances, Earth's surface will continue to cool, water will arrive and remain, and chemistry will take its first irreversible steps toward biology. The stage is nearly set for the origin of life.
As Earth continued to cool, a subtle transformation began to reshape its destiny. Water vapor released by relentless volcanism condensed as temperatures dropped, falling back to the surface as rain. Over immense spans of time, oceans formed, covering much of the planet and stabilizing its surface conditions. Water did more than fill basins. It absorbed heat, moderated temperature extremes, and became a powerful agent of change. Through erosion and chemical interaction, it began reshaping rock, initiating cycles that would define Earth's geological eras. Far into the future, the atmosphere evolved, dominated by carbon dioxide, nitrogen, and water vapor. It bore little resemblance to the air we breathe today. Yet this early atmosphere played a crucial role, trapping heat and preventing the planet from freezing under a faint young sun. Extreme events remained common. Volcanic eruptions, massive storms, and frequent impacts continued to disturb the surface. But now, Earth had buffers. Oceans and atmosphere worked together to soften extremes, turning raw violence into manageable variability. This balance was fragile, not guaranteed. Slight changes in distance from the Sun, planetary mass, or atmospheric composition could have rendered Earth lifeless. Science shows that habitability is not a single factor, but a network of conditions, holding each other in check. Here, the planet began to behave like a system, rather than a collection of parts. Energy flowed, material cycled, and feedback loops emerged. These processes would later regulate climate, influence supervolcanoes, and guide long-term planetary stability. Long before life appeared, Earth was already practicing resilience. It was learning how to recover from disruption, how to maintain liquid water, and how to sustain chemical complexity over time. As the cosmic calendar moves on, this stable yet dynamic environment will allow chemistry to cross a critical threshold. In Earth's oceans, molecules will begin interacting in new ways, setting the stage for the origin of life itself.
In Earth's early oceans, chemistry crossed a quiet but irreversible line. Simple molecules, energized by heat, radiation, and chemical gradients, began interacting in increasingly complex ways. This was not life yet, but it was no longer just inert matter. The planet had become a laboratory where reactions could build upon one another. Energy flowed constantly through this system. From hydrothermal vents on the ocean floor to shallow waters warmed by sunlight, Earth offered countless environments where molecules could assemble, break apart, and assemble again. Science shows that repetition under stable conditions is a powerful creative force. Some molecules began to store information. Others catalyzed reactions, speeding up processes that would otherwise stall. When these functions overlapped, information and catalysis, self-sustaining chemical systems emerged. This was the threshold where chemistry started to behave like biology. Life did not appear as a single dramatic moment. It emerged gradually, through countless failed combinations and rare successes. The first living systems were simple, fragile, and microscopic, yet they carried something entirely new: the ability to persist by copying themselves. Earth's environment made this possible. Liquid water provided a medium for reactions, while geological activity recycled nutrients. Even extreme events such as volcanism contributed by renewing chemical diversity, rather than extinguishing progress. This early life did not transform the planet overnight. For hundreds of millions of years, it remained invisible on a global scale. Yet its presence marked a profound shift. Matter was no longer just following physical laws, it was beginning to exploit them. The origin of life connects directly to everything that follows. Geological eras, atmospheric change, and future complexity all depend on this step. Without it, Earth would remain a dynamic but lifeless world shaped only by physics and chemistry. As the cosmic calendar advances, life will begin altering the planet that gave rise to it. What started as microscopic persistence will eventually reshape oceans, atmosphere, and climate, setting Earth on a path unlike any other known planet. For a long time, life survived quietly, drawing energy from chemistry rather than light. Then a profound innovation appeared. Certain microorganisms learned to use sunlight to split water, releasing oxygen as a byproduct. What seemed insignificant at first would become one of the most transformative changes in Earth's history. Oxygen was not immediately welcomed. It was reactive, even toxic to early life forms. As it accumulated in oceans and atmosphere, it triggered a planetary crisis. Many organisms vanished, but science shows this was not destruction without purpose. It was transition on a global scale. This shift, known as the Great Oxygenation Event, altered Earth's chemistry permanently. Iron in the oceans oxidized and settled to the seafloor, changing nutrient cycles and surface conditions. The sky itself began to change, gradually moving toward the atmosphere we recognize today. Oxygen also enabled a new kind of metabolism. Life could now extract far more energy from the same resources. This efficiency would later support larger cells, greater complexity, and entirely new evolutionary paths. Geological eras record this transformation with clarity. Rock layers preserve chemical signatures of rising oxygen, linking biology and geology into a single narrative. Earth was no longer just hosting life, it was being reshaped by it. Extreme events did not stop, but their consequences changed. With oxygen present, weathering, climate regulation, and even supervolcano emissions interacted differently with the atmosphere. Feedback loops became stronger and more intricate. This moment reveals a subtle truth of science. Life does not merely adapt to a planet. Given time, it transforms the planet itself. Earth became a different world because living systems learned how to use energy in new ways. As the cosmic calendar moves forward, oxygen will open doors to complexity unimaginable to early life. The path toward multicellular organisms, ecosystems, and eventually humanity now becomes possible. With oxygen reshaping Earth's atmosphere and oceans, life gained access to unprecedented energy. This surplus made cooperation possible at a cellular level. Single cells began living together, not as loose colonies, but as integrated systems with shared purpose and division of labor. Multicellularity was not an instant leap, it was an experiment repeated many times. Cells specialized, some focusing on structure, others on energy or reproduction. This cooperation allowed organisms to grow larger, survive longer, and interact with their environment in entirely new ways. As bodies became more complex, evolution explored form and function. Movement emerged, sensing improved, and internal organization became more refined. Life was no longer confined to passive survival. It began to actively shape how it interacted with the planet. The groundwork was being laid for rapid diversification, where biological possibilities would expand dramatically in a relatively short span of geological time. Earth's environments encouraged this transformation. Shallow seas, fluctuating chemistry, and stable temperatures created evolutionary pressure without constant catastrophe. Extreme events still occurred, but long periods of stability allowed complexity to persist and refine itself. Geological eras preserve this shift with striking clarity. Fossils begin to show organized bodies, symmetry, and early ecosystems. Biology and geology became tightly intertwined, each recording the progress of the other. This phase teaches something essential about the universe. Complexity does not arise from competition alone, but from cooperation under the right conditions. Progress depended on connection, not isolation. As the cosmic calendar advances, this cooperative life will soon explode into diversity. The oceans are about to fill with forms that redefine what life can be, marking one of the most dramatic transitions in the story of the planet. Across immense spans of time, complexity continued to layer upon itself. Nervous systems emerged, then brains capable of memory, prediction, and learning. Intelligence did not arrive suddenly. It unfolded as an extension of life's long experiment with cooperation and adaptation. On one small planet, in one ordinary galaxy, a species appeared that could model reality in its mind. Humanity learned to observe patterns, test ideas, and preserve knowledge across generations. For the first time, the universe contained beings capable of asking how it began. Science became a new evolutionary tool. Through observation and evidence, humanity reconstructed the history of Earth, the sequence of geological eras, and the chain of extreme events that shaped the planet. Curiosity became a way for the cosmos to understand itself. This perspective matters because intelligence changes responsibility. Knowing how fragile conditions are, how easily life can be altered by climate shifts, supervolcanoes, or cosmic impacts, creates awareness. Knowledge connects action to consequence. Humanity did not step outside nature. It emerged from it, bound by the same physical laws that govern stars and galaxies. The atoms in human bodies were forged in ancient stellar explosions, linking thought itself to the deep history of the universe. Here, the cosmic calendar closes a subtle loop. The universe began without observers, driven purely by physics. Now it contains observers capable of reconstructing that origin with precision and humility. This stage carries a quiet implication. Understanding does not grant control over the cosmos, but it does grant perspective. Seeing the long arc from the Big Bang to life reframes how we value time, stability, and continuity. As this series continues, each episode builds on this awareness, connecting cosmic beginnings to planetary futures. If this chapter resonates, explore the earlier days of the cosmic calendar to see how every step made this moment possible. As intelligence emerged, another realization followed. Nothing in the universe is permanent. Stars burn through their fuel, planets cool, and even galaxies evolve toward quieter states. The cosmos that once expanded in fiery youth is slowly aging, guided by the same laws that once made creation possible. Earth itself exists within a narrow window of habitability. Geological eras demonstrate this clearly. Climates shift, continents drift, and extreme events periodically reset the conditions for life. Supervolcanoes, asteroid impacts, and atmospheric changes are not anomalies. They are part of the planet's long rhythm. Science shows that stability is temporary, maintained by balance rather than guarantee. The same processes that allowed life to flourish can, under different conditions, challenge its survival. This does not make existence meaningless. It makes it rare and precise. Humanity's ability to recognize this fragility is unprecedented. By understanding planetary systems, climate feedbacks, and cosmic history, it becomes clear how small the margin truly is. Knowledge transforms uncertainty into responsibility. The universe does not promise preservation. It offers opportunity shaped by time and physics. Earth has remained habitable, not because it was destined to, but because countless variables aligned and continued to align across deep time. This awareness reframes how progress is measured. Advancement is not domination of nature, but alignment with it, recognizing limits, feedbacks, and long-term consequences rooted in science. Here, the cosmic calendar delivers its single unspoken lesson. Continuity depends on understanding the systems that sustain it. The future is shaped not by beginnings alone, but by how knowledge is applied. As this day in the universe draws its structure together, the story now stands complete. From the birth of space-time to a planet capable of reflection, the remaining question is not how it began, but what follows from knowing.
Even now, the universe is not finished. Expansion continues, galaxies drift apart, stars quietly age toward their final states. The same physical laws born at the Big Bang are still at work, shaping the future just as decisively as they shaped the past. Earth, too, remains in motion. Its interior still circulates heat, continents continue to shift, and geological eras advance. Life adapts, climates fluctuate, and extreme events remain part of the planet's unfolding narrative. Science reveals that the present moment is not an endpoint, but a transition. The cosmos is dynamic, not static, always moving from one state to another. What exists today is the result of deep history, and what comes next will be shaped by present conditions. Humanity lives at a rare intersection of awareness and influence. For the first time, a species understands the forces that created its world and can foresee some of the consequences of its actions. This awareness connects cosmic history directly to present choices. The universe does not pause for reflection, yet reflection changes how a moment is lived. Knowledge of the cosmos reframes scale, urgency, and value. Time becomes precious when its depth is understood. From the Big Bang to now, nothing unfolded randomly, yet nothing was guaranteed. Order emerged through law, chance, and persistence. Earth's story stands as evidence that complexity can arise and endure under the right conditions. This final perspective ties every earlier chapter together. The history of Earth, the rise of life, and the emergence of intelligence are not separate tales, they are expressions of a single cosmic process. As the cosmic calendar completes this day, the universe remains open-ended. The story continues. Written by physics, shaped by time, and now witnessed by minds capable of understanding where it all began.
Understanding the Big Bang is not about memorizing a beginning. It's about recognizing how deeply connected everything is, from the earliest expansion of space to the present moment on Earth. When you grasp this chain, science stops being distant and starts becoming personal. Apply this perspective beyond the screen. When you think about time, think bigger. When you think about change, remember that even the universe evolved through instability. Geological eras, life and humanity itself, emerged not from comfort, but from adaptation under precise conditions. So here's the question worth sitting with. If the universe required balance, patience, and understanding to sustain complexity, what does that imply about how we treat our planet today? And if Earth is the product of billions of years of fine-tuned processes, what responsibility comes with knowing that? If this journey through the cosmos expanded your sense of scale, share your thoughts in the comments. What part of the universe's origin surprised you the most? What idea changed the way you see Earth or humanity? To continue exploring the universe as a living timeline, subscribe to Cosmic Calendar, One Day of the Universe, and activate notifications. Each episode connects another moment in cosmic history, building a complete perspective piece by piece. Carl Sagan once the universe to know itself. Bang to conscious thought. This story is not about dominance or destiny. It's about understanding where we stand in a vast, evolving cosmos.